Everyone, welcome for another training here at Briggs Stratton Energy Solutions. My name is Daniel Moyer. I'm one of the technical trainers here, and today's topic is going to be coupling AC and DC solar to an energy storage system. A couple of housekeeping items before we get started. Their chat has been disabled, but the Q&A is open and ready to use, so put your questions, your comments in there, and we'll take a look at that throughout the talk and at the end to see what's left over. Additionally, this is a NAPCEP accredited course for continuing education credits. So if you're here for your NAPCEPs, you will earn 1 hour. At the end of this hour talk, we will have our email pop up. Please email us your full name, spell it out for me, and I'll make sure to issue you your credits. Speaking of NAPCEP, really exciting. NAPCEP is going to be in Milwaukee in March, which also happens to be the headquarters of Briggs & Stratton. So if you're going to be out for NAPCEP, you can register right there using that QR code. Let me know. We're going to have an event at Briggs & Stratton headquarters, which isn't far from the convention center where NAPCEP is being held. I'd love to have you be a guest of Briggs & Stratton. We're going to do some additional trainings there. We're going to have some food. We're going to give a tour of our museum and also our power lab as well. Really exciting. It's one of my favorite conferences of the year. So as we kind of dive into today's topic, right, a lot of systems out there already have solar modules and a string inverter or microinverters. And by design, a lot of those systems, when they detect that the grid has gone down, they shut themselves off so that they're not backfeeding the grid when the grid is down. And what we can do is we can put in an energy storage system that will create a microgrid in the home. It will disconnect itself from the grid using energy stored in a battery, create that AC sine wave that the string inverter or the microinverter recognizes, and stay alive and continue to operate. So it's a great way to come in and retrofit existing systems that don't require you to get the ladder out to go up on the roof. We're going to leave the microinverters. We're going to leave the string inverters in place. We're going to add usually a hybrid inverter and a battery, and then bring that AC coupled solar in. Now, when we're doing DC coupled solar, that's usually going to be on new installs where we have the opportunity to come in, add that solar up on the roof, keep it DC, feed the DC through a charge controller, and then send that DC directly into the battery. It's more efficient that way. And on a new install, it could be less expensive because we're not buying microinverters or another string inverter, but it can be less expensive on retrofits just to leave the system alone. So we call that AC coupling as well. So we're going to talk a little bit about that. And then we're going to also dive into some of the other new products and new inverter partnerships that Briggs & Stratton Energy Solutions is now partnering with as well. So as we take a look at this diagram, and we share this a lot on our talks here, what do we have, right? Right in the middle is our hybrid inverter. This is where our transfer switch is. This is where our charge controller is. This is where the inverter and the battery charger is. And this is where a lot of the controls are for that time of use controls, the potential for peak demand shaving. And this is also where we bring in the generator. So one thing I kind of like to highlight here is this bidirectional line on the grid. There's a lot of utilities and a lot of states that have now eliminated net metering. Well, at least eliminated net metering that's favorable payback. For example, out in California, we used to have a 1-to-1 net metering 2.0 or NEM 2.0. For every kilowatt hour we send back to the grid, we get 1 kilowatt hour credit that we can use at night or in the winter. With the elimination of that to a net billing tariff, when we send kilowatt hours back onto the grid, we get paid fractions or the wholesale rate, pennies on the dollar, essentially, for that kilowatt hour. What that means now is that when we have solar production during the day, we need to feed that into a battery and then store it in the battery for use at night. And of course, the generator always comes in. In the context of today's topic, AC-DC coupling, this is a prime example where we're taking in DC into a charge controller, we're sending that DC into the battery, and then only when we need to power loads, we're going to turn that DC into AC through the inverter. Now, we can take in microinverters. Those look like some N-phase IQ7 pluses there. Or it could easily be a string inverter, and we can take that AC and feed that into the inverter. Then we take AC, we send AC down to the inverter turns that into DC to then charge the batteries, and then we can take that DC out and again feed it up to the loads as well. Now, if we want to do both microinverters or a string inverter and a generator, it gets a little more complicated, and we're going to talk about some strategies to incorporate that as well. One really exciting news, and this was just launched at RE Plus 2025 last week. And if you were at RE Plus, let me know in the Q&A. I'd love to hear what your takeaways from the show were, and I'll share some of my takeaways a little bit later as well. But EG4 is now an approved inverter partner for Briggs Stratton, not only for our batteries, but also our generators as well. What I'm showing here is a little bit of a more advanced system, I would say, using their grid box. So absolutely, EG4 makes the 18 kPV and the 12 kPV hybrid inverters a lot like the Solarc inverters. But in this example, what I'm showing here is we're looking at the grid boss flex boss combination. So we still have our grid, we still have our loads, and of course, we always have our apps and the monitoring ability. We're taking DC, right? And we're feeding it into a flex boss inverter. So we're turning the DC to AC, and now we're sending the AC back and forth to the grid boss, right? This gateway. And this is a great advantage. What this allows us to do is kind of decouple where the battery and the battery inverter needs to live from where the service entrance to the home is. Usually with hybrid inverters, you want to locate that hybrid inverter relatively close to the service entrance to the house. So we're not running 200 amps of grid over to a hybrid inverter and then 200 amps right back out. This really allows us to decouple that because we can put this grid boss out there, and then we can put the battery inverter charger in the garage along with the batteries. And then all we have is 90 amps of AC passing back and forth between the two, just one set of conductors. Of course, when we bring in DC coupled solar, that's the beauty of this flex box, is that it still has built-in charge controllers. So we can bring in the DC, feed it into the charge controllers in the flex boss, and then charge up our battery. What's great about the grid boss additionally, though, is that it can also bring in AC coupled solar into that grid boss, feed that into the grid boss, which can either be sent up to the home loads, exported out to the grid if you have a favorable net metering agreement, or we can send that AC back down to the inverter battery charger and then use that to charge up the batteries as well. We're going to look at a little bit more detail too, but that grid boss really allows seamless, easy integration of not only AC coupled solar, but also a generator. And I'll share a little bit more details about that here in a minute. So as we take a step back, we talk a lot about AC-DC coupling in the context of how solar modules are sending their energy down into the battery bank. And, you know, I worked at Sunfrost for a lot of years, and I remember about 15 years ago, I was just telling Larry Schuessler about this, the founder of Sunfrost, the first time I read about this concept, and it really didn't make much sense to me. You know, why would we turn DC to AC, AC back into DC? It just seems like a loss. But then when you realize that there's so many homes out there that have existing solar with microinverters, with string inverters, that we need to now start to add energy storage, not only to provide them the resiliency for during backups, but also there might be systems that are aging out and now have expired net metering agreements that are now being forced onto NEM 3.0. So they're no longer getting that favorable one-to-one net metering credit. So we need to now go ahead and store that solar energy that would otherwise be exported to grid and store it in a battery bank for later use in the evening. AC coupling of energy storage, right? So we're going to take AC that comes off of that microinverter, that string inverter, and then put it into the inverter battery charger and charge up the battery. DC coupling, like I mentioned, we're taking DC right off the roof. We have a string of solar modules that's building up that voltage. We're going to take it down into a charge controller, find the MPPT point, and then charge up our batteries with it. And AC coupled batteries, I see in a lot of the industry that you have a battery. Integral to that battery is an inverter charger built in. So it's kind of one monolithic block there. And I kind of call those AC coupled batteries. We're still sticking with the idea that we're not going to do that. I showed that example a second ago where we have a flex box and we have a battery or multiple batteries. And that's the beauty of it, is that we can scale up the amount of batteries, the amount of fuel we have, without having to add additional inverters every time we add a battery module. So I see this more common in the industry, that we're still going to have that kind of AC battery architecture, if you will, where we have a flex box and then we're going to have batteries, but we don't need to add a flex box every time we add a battery. So that allows us to scale power and energy separately, which can be really nice to avoid spending extra money if one homeowner needs more energy in kilowatt hours, or another homeowner might need more power in kilowatts. One of my takeaways at RE Plus was the number of bifacial solar modules. And I was really blown away, the amount there. In fact, I don't think I really saw a single non-bifacial solar module. So as we kind of look at this here, and we won't spend much time here, and because I realize a lot of us already know this, right? The solar cell is put into a solar module, which then goes into a solar array. I probably should update my slide. I noticed a lot of half-cut cells there, right? That's a full cell right there. And then we're showing here, how the physics of a solar module works. And then I found, a great paper by LG, a white paper on what it looks like for these bifacial solar modules. And it's really interesting to read it. Everybody who's attending this is going to get a copy of the slide deck. You can click on that link there. Everybody attending is also going to get a recording of this webinar as well. So when we look at these solar modules, and we're talking about DC coupled solar, the charge controllers built into a lot of the hybrid inverters, or you might still have external charge controllers, they're going to have a voltage range of when the MPPT is, when the charge controller is going to come alive, then the MPPT voltage range. So we have to think about what our modules are, and this is an old, probably 36 cell, 18 volt module here, right? We're going to have to wire these in series to build up that voltage so we can have that MPPT charge controller come alive. Keep in mind that when temperature drops, voltage goes up. When the insolation or the sunlight increases, that's what's going to affect our amps. Now, a lot of words on this screen, but this kind of just reinforces the concept that I was just making, right? When we put things in series, the voltage adds up and the amps or the current stays the same. And then we might need to be bringing strings in parallel. What's great about a lot of these hybrid inverters, like that EG4 18 kPV, like the Solar, is that it has the ability to parallel up strings inside of the inverter itself. We don't need to get the little MC4Y adapters. So there's going to be a couple of combinations, right? I'm giving the example here. We got 10 panels, 5 in series, and then we're going to parallel those up. And this is the voltage that we'll get, right? We need to build up that voltage and then keep our amps below the rating of those MPPT charge controllers. Optimizers are also a big concept here. I want to mention quickly that if you do come out to Milwaukee in March, it's going to be a nice, warm in March Milwaukee day, I'm sure of it. And we're going to walk out to the Power Garage or Power Lab, and we've used Tigo optimizers. Tigo makes rapid shutdown devices. We chose the TS4Os, which not only gives us the rapid shutdown, but also that optimization that allows module level monitoring. If we don't have any shading out there, but if we did have shading or voltage mismatch, those optimizers are going to eke out the most power out of that array. You do come out to a lot of systems with solar edge optimizers. Keep in mind with solar edge optimizers, those need to be used with the solar edge inverter. So I'll show you an example here in a second. We're just going to not even touch that. We're going to take the AC out of that solar edge and send it right into the hybrid inverter, like an EG4. I guess where I'm going with this is that it might be tempting to go up to the roof and or just rip out that string inverter and make it a DC coupled system. And that might be possible. We might be able to take that DC that was otherwise going to a string inverter and now just feed it right into the charge controllers on the EG4 or on that solar. When you do that, though, there might be some code implications. You might need to add rapid shutdown to the roof. And the panels might not be wired in a series parallel configuration that's going to allow you to work with the charge controller that you got. With microinverters, that's a bigger proposition, right? We're talking about going up to the roof, lifting up every panel, removing the microinverters, restringing it, and then sending it back down. In a lot of those examples, I would just leave the microinverters in AC couple. Here's an example, right, of what it looks like when we're doing a new install with those microinverters. That looks like, to me, some Iron Ridge racking. Again, those are almost certainly end-phase microinverters right there. And we're feeding DC in these guys here. And then this is our AC trunk cable that we're sending 240-volt AC along. And then we're coming down the roof, feeding it AC. We feed that AC into our IQ combiner box up here. This right there, I think, is a breaker just feeding the IQ Envoy that's inside there. And then we're feeding off back to our main electrical panel to a backfed breaker. In an AC coupled system, we would simply intercept this that would otherwise be going back to the main panel backfed breaker with the lockdown kit at the bottom of the bus bar. We're now just going to feed that into the hybrid inverter, usually on the gen port, but there is ability to also land that on the loads port in a load center as well. These are optimizers. I'm not sure what brand these are, but I really don't like this install. You can see here that they're laying right on top of the roof, so there might be some heat implications here. But this is going to keep it DC, right? We're going to feed DC into this optimizer. We're going to keep it DC as we string them together and send DC down off the roof. You know, back in my old Sunfrost days, we used a lot of PWM charge controllers. Then 15 years ago or so, charge controllers were expensive, inverters were expensive, and we would use those. But now it's incredible to see how cheap you can get some of these MPPT charge controllers. And, you know, I'm not always a fan of going with the cheapest products, right? Just like our batteries aren't the cheapest on the market because you're paying for what you get for. So I'm looking at, you know, this one, I think I found this on Amazon here. But what I really liked was Morningstar charge controllers, Victron charge controllers, definitely. Midnight Solar, right? What these are able to, and I showed it earlier in the graph, instead of switching, like a PWM is just going to switch on and off really quickly to kind of control that voltage, where an MPPT charge controller can track where we're going to get the most power when we multiply our volts times our amps coming off of that solar module. You know, and I also mentioned here wind and hydro, you know, at RE Plus, and let me know if you were at RE Plus. I didn't see a single hydro built-in wheel in the entire show hall, or a small micro wind system as well. And I think that's just due to the fact that solar modules have become so less expensive over the years. So this is that example with that the PWM charge controller that I was talking, how we're just turning it on and off really quickly using FETs. I really liked the Sunsaver, this model specifically because it also came with a low voltage disconnect, so we could turn off loads before we drain the battery too much. And that was back in the day when we still had a lot of DC loads, right? A DC Sunfrost or some DC light bulbs as well. This is a good fit for smaller systems, but I think in a lot of the industry, we've moved past that and we've gone towards MPPT charge controllers. And like I mentioned earlier, that we're kind of riding the curve here where we're going to eke out the most amount of power out of a solar module by finding the optimized spot of our amps times our volts at that maximum power point. It's also interesting to see, back in the day, we did have separate charge controllers, separate MagnaSign inverters, separate automatic generator starts. But what's really exciting is a lot of these hybrid inverters have it all built into one device. Victron, notably, is still an exception, and I had a great time going over to the Victron booth. They still have all the parts and pieces, and I can appreciate that to some extent, especially in the mobile market or the marine market, where a hybrid inverter might not be what you need. There might be different parts and pieces, make it more modular to make the system work for what your specific application is. So what lands on the DC bus, right? So one of my kind of favorite new products out of Victron is this Lynx Power In, and these have Class T fuses in them, and we can bring in our batteries. In this example, we're looking at our Phi 3.8 Briggs Stratton batteries. These are great for lead acid battery replacement. And then we're bringing in our solar through an MPPT charge controller, and then we're landing that all on the DC bus. And then we're taking that DC, we're feeding it up into the inverter that can then turn that DC to AC to power our loads. And additionally, we could also use this as a battery charger where we could use grid. Maybe we don't have solar at all. We could use this AC coming off the grid to charge up our batteries using the Quattro right there as well. One really big excitement at the RE Plus show was Solarc released the 18K PV inverter. Long time coming. I've really been waiting to talk about this. If you look at it, it looks exactly like a Solarc 15K. It is a little bit taller. They added a little bit of extra space down here. What you can't see also is that they moved the neutral bar. If anybody here is wired up one of these, it can be really hard to get the neutrals and the grounds all landed in there. So they've actually turned the neutral bar vertically. Previously in the 15K, it was horizontally. So it makes those neutral connections a lot easier. If everyone remembers, a Solarc 15K could do 12,000 watts from battery to load, and it could do 15,000 watts if PV was also contributing to that. With the Solarc 18K, it's now what I'll say a true 18K, where now we can do 18,000 watts from batteries to loads continuously. And look at that surge rating, right? 36,000 watts, 150 amps. That's incredible. So now we're able to start a lot of those large motors that we find in large air conditioners. No problem. Get that motor started without necessarily having to put a soft start on it, and then get it going. And then of course that compressor is going to ramp down at its run watts. When we talk about bringing in a lot of AC or DC coupled solar, 40,000 watts. I mean, that's incredible to think that somebody would need that much solar. But yes, absolutely, we can bring that in there as well. One of my favorite trainers in the industry is John Cromer. Next week on Tuesday, John Cromer is going to be leading a live webinar. I encourage everybody on here to join that. I put a QR code right there. Additionally, there's the URL or the link to register for this. But John Cromer next week is going to go through all the details on this 18K PV from Solarc. stay tuned. Really excited to see some systems going in with this. Promise I'll show you some solar edge. So, well, first off, I'm pretty surprised that these solar inverters are still even operating, but they are. Up top on the roof, where this conduit is going, you can see your PV label stickers here. There's modules, there's optimizers. We're sending that DC down the roof. These two inverters are turning that DC to AC. We're landing in a combiner here. There's probably two 20-amp breakers, and we're probably lug fed over here, and we're feeding into this Solar 15K onto the gen input. Down below, these are our 6.6 stacking batteries. So we have two stacks of two, and we're bringing in, so each one of these is coming, we have pre-punched knockouts for 2-inch conduit, bringing that on here, and we're feeding that DC right into the Solar 15K, which has dual battery inputs as well. Down below, we do have our optional energy track, which is our in-house monitoring system. Of course, the EG4 is going to have its own monitoring platform. But if you're looking for that more granular data, or if you're looking for somebody that really likes to look in the batteries, more specific detailed levels, we offer energy track. And there's some exciting news coming about this energy track paired up with our generators as well. Let's check. Michael's asking, what is the pass-through amps on the gen port for the 18K? That is a good question, and I will look that up. I don't know the answer. That's a great question, right? When we're talking about being able to bring in a larger generator or more AC coupled solar as well. So this is a typical Enphase system right here. We have our solar modules, we got our microinverters, we're bringing it down to our IQ combiner, and then we're sending the AC right out of these microinverters down the roof into here, which is monitoring it, right? We got a little Envoy built in there, and then we're sending it back to a breaker, a backfed breaker with a lockdown kit located at the bottom of that load center right there. DC coupled, right? The idea here is that we're bringing DC down. We have these are AP Smart rapid shutdown devices. These ones, I should change my picture. These ones are meant for 2 modules each, but they sell one from 1 module each. We're bringing that into our MPPTs, down the MPPTs into our battery. We have our backfed breaker still over here, and then we're able to bring our 50 amps up here for our critical load subpanel. We do have a 2-wire signal to start, and you don't necessarily need a breaker here because the generator has the built-in breaker, but some code AHJs might want you to put in an additional breaker. So this is what it looks like when we're bringing in AC. Remember, we have that AC, those micros, the IQ combiner, and now we're bringing that into the solar on the gen port right here. And then what we have is still our battery right here. Now notice, and I could have done this on the other slide, is that when we're backfeeding, say a load center with a 200 amp main and a 200 amp bus, the NEC 120% rule says the largest backfed breaker we can have is 40 amps. What's really cool about these newer hybrid inverters is with that PCS or CRD listing on their UL 1741, which says that we can put in a larger breaker than 40 amps, and that we trust, because UL tested it, that yes, it can draw 60 amps out of the load center, out of grid, and send it up to our critical load. So we're making sure we can pass through 60 amps right here, but we're never going to backfeed more than 40 amps. And that's a really cool feature, so that we can not be limited by that 40 amp breaker like we were with that 120% rule when we didn't have PCS CRD control. So the concept here is when the grid goes down inside of the solar, within milliseconds, the solar is going to disconnect from grid. using energy stored in the batteries. It's going to form a grid that the microinverters recognize and continue to operate. When the batteries start to get full, the solar will start to use frequency shifting to raise the frequency of the sine wave to curtail the AC microinverter's output so we don't overcharge the batteries. And we call that frequency shifting. Get a little more fancy here, and you can absolutely do both. I'm thinking of a situation where you would have a system where you come out, add a hybrid inverter, add some batteries, and they have existing solar over here, AC coupled solar. And what I want to do is be able to add more solar here and have it be DC coupled. Now, I don't want to put my foot in my mouth, but there is some people out there that have NEM 2.0 or a really favorable net metering agreement where they're still getting that one-to-one credit. And the rules say you can't add more solar to a system that under NEM 2.0 or you'll lose it and you're going to get kicked off to NEM 3.0. But there is some opportunities here where you can add more solar and then set it up for non-export. So I want to be careful on how I word this because not every system is able to do that. And there might be situations where you need to have separate inverters to do this, but this concept is possible to have non-export systems and keep this existing solar just feeding back to the grid, build in all your credits, and then have a newer system not exporting, helping to keep a battery charged, helping to support the home's loads. So we're looking here at a single line diagram of a solar, and we got our grid, we got our meter, we got some CTs here, and these would be necessary if we wanted to measure the energy consumption of any loads that are not backed up, especially if we wanted to program an inverter to backfeed just enough to support loads here, but not send any more than what would go back out onto the grid. Grid port, right? So we got 200 amps coming into the grid, 200 amps coming right back out of the load, down to the load center. And then we have our AC coupled microinverters, our N phase. This is our IQ combiner right here. And we're just feeding it in onto the gen port. That's exactly like what we would work with. And Michael was asking, you know, on this is the Solar 15K, we can do 19.2 kilowatts of continuous AC solar or a generator here. And we'll have to get the update on what that is on the Solar 18K. Here's our DC coupled solar, and here is our battery bank. And what's cool about the Solar 15K and the EG4 inverters is that they have dual battery inputs. So that allows us to have 2 stacks of battery without having to have an external combiner. Looking here on the inside of a solar 15K, here is the grid coming in. Here is our load going out. Here's the generator coming in. Now, we could also have the AC coupled solar there. We could also have it be a smart load output where we can program the solar that once the batteries get to a certain state of charge, let's say maybe 90%, let's go ahead and turn on that port, power luxury loads like maybe a hot tub. And when the batteries start to drain, maybe below 50%, we can turn this port off. So this can not only be an input from generator or AC coupled solar, but it can also be an output as well. Notice the neutral bar here in that horizontal position. In that 18K, it's now vertical. These are the accessory pinouts. This is where our battery communication is going to be. Parallel comms is if we're going to have multiple inverters, battery inputs, and the battery breakers are on the left-hand side. If we're going to be wiring those CTs go into pins 3, 4, 5, 6. Our rapid shutdown button is going to be on BB. All of these batteries in the market, even our 6.6 stacking battery, still have closed loop communications. We want the batteries and the inverters to be talking to each other. There's a lot of data that's transmitted on this closed loop CAN bus. For example, the battery is telling the inverter its state of charge, its temperature, its physical capacities, and what the Solarc or the EG4 inverters can do is take that information and then auto-populate set points inside of the inverter, but also determine when and if we need to start curtailing battery charging during cold weather events so we don't damage the battery as well. Mentioned earlier that we still do have what's known as energy track, and we'll have a more upcoming training where we'll dive more into the details of that. If you are going to have energy track, you're going to come off of the RS485 port inside the 6.6 controller, which is that top part that goes on the battery stack. Out of the CAN bus, we're going to come out of our battery controller out of the CAN port, run up to the Solarc. There is a crossover dongle that we include. That dongle is the same dongle whether you use a Solarc or whether you use an EG4. Made it easy for you. Otherwise, if we didn't have that crossover dongle, you might have to become a network technician and start making up your own Ethernet cables and crossing over some of the wires to change out that pinout configuration. We're looking at the top of the controller up here, negative, positive. This is what's going out. That black Ethernet cable is going over to the inverter. That white Ethernet cable is going over to the energy track. There is an optional grounding here. A lot of AHJs wouldn't require that. If we're going to have multiple battery stacks on a single inverter, we're going to still come out of the CAN port up to the inverter, still out of the RS485, going up to the gateway, energy track gateway if you have it, and we're just going to simply daisy chain the Ethernet cables along. If for whatever reason you're not using energy track, you're going to want to put the end terminal or a plug. It's a little orange plug, and what that does is close the CAN bus loop. So there is a terminating plug that would go in here if you're not going to be using the gateway. All of the ports, communication ports on these batteries need to be connected to something, whether it's the Ethernet up to the Solarc, whether it's the Ethernet to the gateway, or whether it's a terminating plug. I still like that a lot of the inverters, including the EG4, and even that FlexBoss has an optional display, still has a screen. And we're kind of looking at a training wall that we had built, right? So grid would come in here, non-backed up loads. We're coming off here, feeding into the Solarc, feeding back out of the Solarc down to our backed up load center. And these light bulbs just represent the presence of grid and presence of backup. A lot of times we have a wiring trough here underneath the Solarc, and we still have a screen, which is really cool. So we're just going to talk a little bit about how we're going to turn a system on. The first thing we do is we're going to turn on the battery. There's a power button at the top of the battery stack on the battery controller. It's going to turn on the battery. Then what we're going to do is, usually the best thing is to get out your multimeter and check to make sure everything is looking good up there for the DC voltage. We're going to turn on the battery breakers inside the Solarc. That inrush of current into the capacitors into the Solarc may cause the battery to reset itself, but it will just come back on and finish charging up those capacitors. Great. Battery's on, Solarc's on. You think the Solarc's on, but we still have to press the power button on the Solarc on the side to get the Solarc to come on and start outputting AC power. As soon as you give that Solarc DC from the battery, the screen will light up. You'll think you're good, but you still have to hold the power button on the side of the Solarc to get the Solarc to come on and stay on and start outputting AC power. We're going to make a couple of programming choices. We're going to want to make sure that we use bat %. That's going to make sure that the battery and the inverter are using SOC to determine when and if we want to charge or discharge the battery. BMS lithium bat, that's 00, and the activate battery. Now, somebody asked me this earlier in another webinar, and a lot of times I would just say, make sure you check activate battery and then just go to the next slide. So I want to take a moment because I think it's a good topic. Let's say, for example, inverter's on, battery's on, and you start to drain the battery, and you don't have a solar, you don't have generator. The battery starts to drain and drain. At some point, the solar is going to give off an alarm. At some point, the solar is going to turn off the AC loads. If that happens, the solar still has a parasitic draw, right? You're still needing to feed the solar some power to keep it alive so that if the solar does come back, it can start processing that and charge up the battery. But if for whatever reason that solar stays on and continues to drain the batteries with its parasitic load, the battery is going to go into a self-protect mode. So what we want to do is when we select activate battery, that's going to tell that when the grid comes back and turns on that solar, that it will send a signal to the battery to activate the battery and let the battery know to come back on. A lot of these charge set points and discharge set points will be automatically populated in the Solarc. And what's interesting here, and I'll just share this with you, is that the Solarc 15K can do 275 amps continuous. All right, you can do 12,000 watts from batteries to loads. A single stack of 3 6.6 batteries with the controller up top can do 14,000 watts continuous. That's perfect, right? If you got a Solarc 15K, you can have a single stack of batteries of 3, and we're good. We know that the battery's output capabilities is quick enough, the C rate is quick enough to support a Solarc 15K. But that Solarc 18K, now that it can do 18,000 watts from batteries to loads, I would say the minimum stacks you need to support of 6.6 batteries to support a Solarc 18K is going to be 2 stacks. Because if you go in there and you put a single stack of 3, a full stack of 3 6.6s, which is 20 kilowatt hours, just under, it's only going to be able to discharge 14,000 watts, which is going to be robbing the Solarc 18K of 4,000 watts. And where I'm going with this is that this should automatically be populated here with that closed loop communication right here. But I would always recommend that you double check these values, make sure that that closed loop communications is set. And as I'm saying that, I don't think that's going to be a big problem. If you have an 18,000 watt inverter, you're probably going to want more than just 20 kilowatt hours of storage. So most of those systems are going to have multiple stacks of batteries anyway. As we look here, this is setting the percentage at which we're going to start a grid charge, the rate at which we're going to charge grid, and then also at what rate will we charge the generator. These are the figures that I was talking about earlier, about the alarm, the shutdown, and then at what percent would we start the battery back up when it's been recharged. And that's a little different than the activate battery. That's when we're going to turn the loads back on. Going back to the topic at hand, if we are going to be bringing AC coupled solar in, we need to go into the BAT setup, go to smart load, and let the Solarc know that we're bringing AC coupled solar into that gen port as well. And then we're also going to use these percentages to let the Solarc know as soon as the batteries start to get about 90% full, we're going to want to curtail some of that AC coupled charging. We don't want to wait till we're completely full. And then as soon as the batteries are below 80%, we're going to go ahead and let that AC coupled solar start charging. And we leave a little differential there just so we're not flipping them on and off. That's where grid cell, that's where we're going to be able to limit the amount of power we sell back to the grid. That's where that 120% rule from the NEC came into play. Any questions? Has anybody done this? Please put that in the comments and let me know. So we're looking at that same diagram that we looked at before with a couple differences. We're no longer bringing the AC coupled solar here, right? What we have is our grid, our meter. We have a transfer switch, and this is a Briggs and Stratton transfer switch right here, and we got our Briggs and Stratton generator. Load grid coming in, loads coming out, DC coupled solar battery. So imagine the batteries are going low. What we're going to do is we're going to send a 2-wire signal to start to the generator. The generator is going to start up. It's going to, normally this transfer switch would be running up and down. It's going to tell this transfer switch to transfer. And now we're going to be bringing in generator in on the grid port. And we're going to take over the loads and we're going to charge up the batteries. Easy. What can happen though is when we try to AC couple solar, so we bring in our AC coupled solar, and earlier I had mentioned, we use frequency shifting to curtail the charge of microinverters or string inverters. So all these hybrid inverters are grid following when they're running off of the grid, and they're grid forming when they're running off the batteries. And when they're able to form a grid when they're running off the batteries, that's when we have the ability to do frequency shifting, and we can shut off the AC coupled solar to prevent the batteries from being overcharged. In this example, when we start that generator, the generator coming into the grid port, as far as the solar arc is concerned, that's grid, and it's going to revert back to a grid following situation. And the danger here is that the AC coupled microinverters are going to recognize and latch onto the sine wave being produced by the generator and want to try and backfeed the generator. So what we need to do is we need to make sure that if the generator is running and the AC coupled solar is producing, we need to have a lockout module or a relay or something to be able to shut that AC coupled solar off. It's not very common, right? Why would the generator be running if the AC coupled solar is producing? I kind of think of a cloudy day where the batteries are drained. So we start the generator and then all of a sudden the clouds go away and that AC solar is now blasting away. So the two ways, we have a Symphony lockout module, or we also have PSP makes a lockout module as well. Gen starts on pins 7 and 8 inside that solar arc. Inside our generators is pins 4 and 5. So I'm really excited about the EG4 partnership. We also launched partnerships with Solus and also Mega Revo inverters as well. Today, I want to focus a little bit on the EG4 product lineup. On the left are their two hybrid inverters, 18K PV and the 12K PV. But what in this kind of context and AC-DC coupling, I want to focus a little bit more on the grid boss flex boss combination. So what EG4 did is, instead of having 200 amp pass through in and out and the ability to shut that on and off, they took that and put it over here in the grid boss. And they kept the charge controllers over here. They got rid of the gen port over here, and they kept it all over here on this side. So essentially all the flex boss is doing is acting as the charge controller, acting as an inverter and a battery charger, so that we're positioning this close to the battery wherever it may be in the house, and then simply running AC between the flex boss and the grid box. Let me break that down a little bit more. I know there's a lot here on this page, but let's just walk through it. The grid boss, in a lot of ways, brings value to the system. So we still have grid coming in. What's cool about the grid boss is that now it has a service rated entrance disconnect. It doesn't come with it. You got to buy it and add it, but it's really easy to install. Before, with that solar, we would have had to have that an external device. We got grid. We're bringing grid in here, right? We're sending grid down in here, down to our backed up loads. We're sending it to our non-backed up loads. We're sending it over to our smart ports, which is built in. And we're also sending it down to our hybrid inverters. So here are those flex bosses, and our batteries would be sitting right over here. So if grid goes down, right, what's going to happen is the ability for this relay to open up and then prevent us from backfeeding any of our, we're going to be running off of our stored energy in our hybrid inverters. We're not going to be backfeeding the grid. I can, Michael, answer. The grid boss has 125 amp generator input, so that's 30,000 watts coming in. Another value add is that what we have also is a manual bypass. So if for whatever reason the whole system goes down, we can manually bypass the grid boss, those flex bosses, and bring in the grid directly to our, well, the grid's also going to be already going to be flowing into non-backed up loads, but now we can bring it down here into our backed up loads as well. AC coupled solar makes it really easy. We're going to bring that into a smart port on the grid boss. We can additionally bring in these smart loads, which will open up based on the state of charges of the battery. One value add here is that if I had multiple inverters, I would need load centers to combine their AC output and their input. That's all done now internally in the grid boss. So remember that example of the generator running, right? So the generator started up because the grid's down, the batteries are low. We're going to feed generator power up, right? The grid's down, that relay opened up. Generator power is going to come up. It's going to go down and back up all the loads. The generator power is now going to flow down into our FlexBoss inverters and start charging up our Briggs Stratton batteries. But notice what happened over here. Where that PV, AC coupled PV was, that relay automatically opened up. So that eliminated the need for us to have an external PSP product or an external Briggs & Stratton relay. It's built in. It also opened up all these smart ports because these should be a lot of your luxury loads here. We are really excited about our 6.6 stacking battery. Like I said earlier, they're cheaper batteries on the market. What makes the 6.6 battery stand out from our competition in a lot of ways is the quick discharge rate, right? That's C/2 discharge rate. You can go even quicker, right? This is C/2 charge rate here. We can go a little bit quicker on the charge rate as well. The ability for it to be a long cycle life, the 130 pounds per battery, so it's easier to stack. You don't have to go out and buy a dolly to lift our battery up. I'd say the look of the battery. What also makes a stacking battery a great product, and there were a lot of stacking batteries at RE+, don't get me wrong, it's also, in a lot of ways, the company that stands behind it. So Briggs & Stratton, being a 115-year-old company, American company, understands the market here in the North American marketplace. We put wall brackets that are designed for wood stud walls, not concrete walls. We have knockouts built in that allow easy 2-inch conduit to be attached. Our tech support team is not just reading off of prompts and in a different country, right? We're here to support you as an installer and make it easy for you. Our warranty is backed by an American company that's been around. We now have a 15-year warranty on this battery. We just announced that at RE+. Unlimited cycles, no throughput at 100% depth to discharge. So some company that may have just popped up 2 years ago offering a 10 or 15-year warranty, who's to say they're going to be around? But we will be. You can stack up to 6 stacks of 6.6s in a system to bring you up just to 120 kilowatt hours of storage. Remember that 18K, right, is going to draw a little bit more than what a single stack of 3 can operate on. So you'd want at least 2 stacks. You don't necessarily need 2 stacks of 3, right? I'm looking over here. We could do a stack of 3, which would give us 14, and a stack of 1 here, which would give us 6.6. 6.6 has definitely been a game changer for us. We've had it out for 2 years and amazing success. It's outdoor rated. It has the ability to go down to 14 degrees ambient charge rate without any heaters. Of course, if you need heaters, we have those available on the Amplify and Phi batteries. And we also have high voltage batteries as well. That was a big topic at RE Plus. A lot of people starting to think about the changes in the marketplace coming with the commercial storage tax credits still being there. So, and also there was a lot of talk at RE Plus about TPOs and PPAs as well. So I'm excited to see what kind of financing is going to be available from a lot of these companies coming out. Let me know what your takeaways were at RE Plus if you were able to go. Both the 6.6 Amplify have 15-year warranties. The Phi, which is a great lead acid battery replacement that still comes in 24 volts, is a 10-year warranty. This is a picture of looking at our high voltage batteries. The reason they're called high voltage batteries is because we run them in series, right? All of 6.6s or the Phi and amplifiers are all going to be wired in parallel. But here we can wire batteries in series to build up the voltage. As we close out, I'd like to invite any installers on the call. I should have updated this. This promotion just ended here. But we are offering $1,000 off your first install, whether you're part of this program or not. We'll give you $1,000 to install your first system. Once you do install a system and we can do some training with you, we'd welcome you into our IQ installer program where you're going to get $100 back on every battery you install. We're going to offer trip reimbursement charges. We're going to offer you leads, right? We're going to put you on our locator maps as well. So as we close out, I want to just say thank you for everybody who's out there installing our batteries. Please, if you've done it with the Solar, let me know what your thoughts are on the EG4, the Solus, the Mega Revo partnership. I see some of our competitors' batteries saying that we partner with every inverter out there. Our battery can work with any inverter. I'd say Briggs Stratton chose not to do that. We have been working with SolarArc very closely for a long time. But what we did is took a very deliberate and slow path on bringing on additional inverter partners. We wanted to vet that partnership, not only to make sure that we work together collaboratively as business units, but also technically, right? And on the engineering side, we had our batteries working with their inverters. We wanted to make sure that all of that closed loop communication worked properly. We also wanted to make sure that we're able to support you as an installer with integration guides that tell you how to program EG4 inverter when you're pairing it with our batteries. And that takes time to get right, and that's exactly what we did. So really excited, EG4 partnership, Solus, Mega Revo, and of course SolarArc with that 18K PV. If you're here for your NABCEP credits, please email energystoragetraining@basco.com, energystoragetraining@basco.com, and I'll make sure that you get your NABCEP credits. If you're going to be out there in Milwaukee at the NABCEP conference, let me know. I'll make sure you get an invitation to our private event that we're going to be having at our headquarters. With that, let's take a look at any questions we might have. So Larry's mentioning, my understanding is that AC coupling voids warranty on solar edge inverters. Is that the case? I am not sure. I would have to check on that. Yeah, so that brings up a good point, right? So not all string inverters, not all microinverters are able to be AC coupled. There might be warranty implications. There might also be so old of string inverters and microinverters that they're not able to respond to that frequency shifting that I was referencing earlier. So make sure you check to see if you're going to have any warranty implications or if those microinverters or string inverters are capable of being AC coupled on that engineering technical side of things. Paul is asking, I'm going to email everybody a link to YouTube where this video will be uploaded of this training, so you'll be able to see that there. Greg saying thanks for the presentation. Yep, of course. Thank you, everyone, again. Let us know if you're going to be at NABCEP, and we'll see everybody at the next time. Take care.